All right. Calm yourself. Got you hot, I know. All right, so we need to talk about how to identify spanning trees, how to draw spanning trees, and how to determine how many different spanning trees you can actually get from a picture. So let's first talk about the basics. Is the following graph a tree for 1A?
No.
Why?
It's closed.
They're circuits, okay? So in order to find a spanning tree, I need to use some of these edges and just connect my points and get rid of the circuits. So how many vertices do I have right now?
7.
I have 7. How many edges do I have right now?
1, 2, 3,
9. 9. Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges. Okay, in order for this to be a tree, how many edges do I need?
6.
I need 6. I need this to be 6. So how many do I need to get rid of?
3.
If I started with 9 and I need 6, I need to get rid of 3. 9 minus 3 is 6. So I don't know where people are getting 2 from. Come on now. Okay, this is something called your redundancy. Bless you. I was thinking for a second. I'm like, wait a second. Hold on. Redundancy. Okay, so what I need to do is remove 3 of these lines to get rid of my circuits.
The one that goes to A to D.
Okay, you said you want to get rid of the one that goes from B to D. Okay, we're going to get rid of this one. You said A and D?
Yeah, I said A and D.
Okay, let's get rid of this one.
And F to C. And then F to C.
F to C. Okay, let's get rid of this one. So, in other words, now I've got this line we kept. I kept this line, and this line. There's your spanning tree. Yes. Okay, so you can always use the redundancy to determine whether you need to remove any lines or not. So let's take a look at the 1 and 2A. How many vertices do I have in this picture?
7.
How many edges do I have in this picture? 6. Do I need to remove anything?
No.
No, this means my redundancy is 0. So this is already a tree. I don't even need to do anything. This is a tree. Okay, so when you have a tree, your redundancy is 0. If it's not a tree, your redundancy or how many lines do I need to remove to make it a tree? Questions right now? Okay, so we've already talked about this. Redundancy. Your actual equation for it is R equals E minus B plus 1. I never remember that formula. That's why I told you it's how many edges you need to remove to make it a tree. You know that your edges always have to be 1 less than your vertices, so you should be able to tell me what the redundancy is without it being a formula. If your redundancy is 0, we have a tree. If your redundancy is greater than 1, we have not a tree. So the first thing you're going to need to do is figure out how many edges do I need to remove. So just like we did with the other one, how many vertices do I have in this picture?
8.
How many edges do I have in this picture? 8. How many do I need to remove to get this down to 7?
1.
I need to remove 1. So that's your redundancy.
C to D.
1 edge. Okay, so now there are several different ways that I can get rid of that circuit. I heard somebody say I can remove edge C to D. What else could I remove? I could remove H to C or C to H.
And then H to D.
H to D. So this means I have 3 spanning trees in this picture. I could remove any one of these 3 edges from this circuit to create a tree.
So you remove the edges that create circles?
Yes. Because our goal is to get rid of those circuits. Okay. Questions on that one? Because as always, it always gets harder. This is the simple one. Now we're about to get just a little bit harder. Not much.
I like this one.
A little bit. Okay. So how many edges do I need to remove in this one? First off, how many vertices do I have in this picture?
8.
8. How many edges?
9.
I have 9. So what is my redundancy?
2.
2. I need to remove 2 edges in this picture. How many circuits do I have?
2.
2. Okay, I've got this circuit, so I need to remove 1 from this one. And I've got this circuit here, and I need to remove 1 from this one. Okay, well, in this first circuit, I can either remove side C to D, I could remove side C to H, or I could remove side H to D. Okay, those are the 3 sides that you gave me from the first one. C to D I could remove, C to H I could remove, H to D I could remove. In this second circuit, what can I remove?
G to D.
G to D,
D to E.
D to E,
E to F.
E to F,
G to F.
G to F. You've got 4 sides in this circuit. I've got side that goes from G to D. I've got a side that goes from D to E. I've got a side that goes from E to F. And I have a side that goes from G to F. Okay, so I've got to remove 1 from this circuit. I've got 3 options. I can remove 1 from this circuit. I have 4 options. 3 times 4, 12 spanning trees. There are 12 different spanning trees.
Where did you get 3 times 1?
The 3 from the first circuit, the 4 from the second one. So these are my options. I can remove CD and GD. Or I can remove CD and DE. I could remove CD and EF. I can remove CD and GF. So those are 4 options. Then I can move over. I can remove CH and GD. CH and DE, CH and EF, CH and GF.
Yeah.
Yes, ma'am.
Adriana Torres, could you come to the front with Keith?
Sure. Okay, so those are your next 4 options. And then finally, I've got these last options. I can remove HG and GD, HD and DE, HD and EF, HD and GF. So that's where all of your options come from. I can remove 1 side from the 3 and all 4 sides of the next one, or another side from the first one and then one of the other ones. Okay, so when you have two separate circuits, you multiply how many options you have for each to get your spanning trees. All right, we're going to do some more examples. Okay, we've got one more scenario that can happen. This is my last scenario, and then we're going to practice. Okay, so in this scenario, how many vertices do I have? 8. How many edges do I have? 9. So what's my redundancy? 2. I need to remove 2 edges. Okay, so I have 2 circuits. I need to remove an edge from this circuit, and I need to remove an edge from this circuit. Okay, so in my first circuit, I have how many options in the red one? I have 3 options. I've got CD, CH, and HD. In the second circuit, in the blue one, I have 5 options. I've got DE, EF, GF, HG, and H to D. Okay, those are my 5 options from the other one. So what we did with the last one, all I had to do was multiply the 2 together, right?
Right.
So you would normally start with, well, this is 3 times 15. Or I'm sorry, 5, which gives me 15. My bad. 3 times 5, which gives me 15. There's one problem here. What's the difference between the last one we just did and this one?
The 2 thingies are connected by 1 line.
Okay. I've got a line that they share in common. So to get rid of that, because we've counted it technically twice now, I counted it here and I counted it here. All we do is subtract 1. So we have 14 spanning trees. Whoop, there it is. All right. Are you ready for the practice?
Yes.
Yes. I like that answer. Yes. Okay. Okay. So take a look at number 1. How many circuits do I have in number 1? I've got 1 circuit. How many sides does that circuit have? 4, which means I have 4 spanning trees. I can remove this side, this side, this side, or this side.
What are spanning trees again?
It's a way to draw a tree without having circuits. So, like, I could remove this side and it would be a spanning tree because we got rid of the circuits. Or I could remove this side and it would become a spanning tree.
Oh, 4 ways for it to be a spanning tree.
Yes, there's 4 different ways I could draw that spanning tree. So, in other words, I could draw, basically what you're finding out here is I can draw a spanning tree like this without this side. Or I could draw it like this without that side. Or I could draw it like this without this side. Or I could draw it like this without that side. So there's 4 different ways I can draw this and make it a spanning tree. That's what you're finding out.
Is there ever a way where you can take off more than just one side?
Is there ever a way that you can do what now?
Like later on, can you take off more than just one?
No. You don't ever want to take off more than just 1 here because, again, you've got 1, 2, 3, 4, 5, 6, 7, 8 vertices. And you have 8 edges. So I only need to remove 1. Your redundancy is 1. So you only ever want to remove 1 because of your redundancy. Okay. Number 2, how many circuits do I have? 2. I've got this circuit and this circuit. Circuit 1 has how many edges?
4.
Circuit 2 has? Do they share one in common?
No.
No, so we just multiply. There's 20 different ways that I can write a spanning tree. Because I have to remove 2 edges in this one. Again, your vertices are 9 and your edges are 10. So I need to remove 2. I need to remove 1 from this one and 1 from that one. Number 3, how many circuits do I have?
2 and they share.
2. Here's 1 and here's 2. Circuit 1 has 4. Circuit 2 has
3.
And Yesenia said this time they share 1 in common. So once I get 12, I have to subtract 1. So we have 11 spanning trees. Okay. Again, that -1 only happens when they share an edge in common.
This time they have 4.
Woo! Number 4's got a lot. Woo! But okay. So Kimberly said we've got 4 circuits here. I've got this circuit, this circuit, this circuit, and this circuit. Okay. So these 2 share a line in common. So I would handle those first. So this is a 3 circuit times a 3 circuit minus 1, which gives me 8. So I've got 8 options in that little bunch. And I have 1, 2, 3, 4, 5 options in this one. And I have 4 options in this one. So 4 times 5, 20 times 8.
179.
20 times 8 is not 179. 160. There are 160 different ways to draw a spanning tree from that picture. I don't need you to draw all 160 ways. I just need you to know that there's 160 ways to do that.
So the reason that for the last one that is 3 instead of 4 is because you don't put the line in the middle. I'm confused. Why is it 3, 3 and not 3, 4?
Because each circuit, so this is a circuit, there's 3 lines.
Oh, okay, okay.
This is a circuit, there's 4 lines. Or, 3 lines, not 4. Okay. Anybody else? Questions?
Why
Issues?
did you times all of them?
Think I don't want to say think probability. Remember the word and in math tells you to multiply. So I need to remove 1 from this one and 1 from this one and from this one. So that's what tells you to multiply. And means multiply in math, or means add.
Like I get the multiplying individually, but not together.
You get the multiplying individually.
Yeah, like the 4 times 5 because of the other thing, and the 3 times 3. Okay, but I don't get the 20 times 8. Oh, because it's all connected.
Yeah, it's one big graph, so everything gets multiplied together.
Okay.
So I mean, I could also give you one that looks like this page. We'll go back and do number 5, but let me see if I can catch Kimberly here. Maybe. You're gonna let me do it again? No. Ooh. All right. So I can draw you a graph like this. And then let's do 2, 3, 4, 2, 3, 4, And then I can do another one that's like 1, 2, 3, 4. So I can draw you this graph. So now you've got 3 circuits. So all the circuits, when you do the edges, have to be multiplied together. So this one is a 3. This one is a 4. This one is a 4. So you multiply them all together because you've got 3 separate circuits. And 1, 2, and 3, or in 2 and 3, we only had 2 circuits, so we only had to multiply 2 numbers. If I made 7 circuits, you'd have to multiply all 7 numbers together. Everything that's there has to be multiplied.
Is it kind of like
I kind of want to take it back to the probability. Do you remember doing like probability problems where they say you have 5 pairs of shirts in your closet, you have 7 pairs of pants in your closet, and you have 3 pairs of shoes? How many different outfits can you make?
Yeah.
That's kind of what this is. I've got 3 edges here and 4 edges here and 4 edges here. How many different ways can I handle this? So you multiply everything together, because that you would multiply your 5 shirts times your 7 pairs of pants times your 3 shoes type of an idea. Does that make a little bit more sense?
Yeah.
Okay. All right, friends, let's go back to number 5. All right, number 5. How many circuits do I have? I've got 4 separate circuits. These ones share a line in common, and these ones share a line in common. So we're going to deal with the top 2, the bottom 2, and then multiply together. So here in this one, I would do what times what? 3 times 5. Careful. 1, 2, 3. 1, 2, 3, 4, 5. So 3 times 5 minus 1, 14. So I have 14 different ways that I can do the top 2. I've got this one's 4 times 3. I've got 11 different ways that I can do the bottom 2. Then I need to put them together. So we multiply them together. 14 times 11. You said what? 154. So I have 154 total spanning trees. 154. Who said I'm lost? What's the matter? One's like, do you need me to help? He's like, for once, I'm totally on it. I'm so proud. So proud, everyone. Anybody else questions that you can formulate for me to answer? Or we can just try to hash it out and I can try to comprehend and
what's 4 times 3 times 6?
Okay. This one. Number 6. How many circuits do I have?
Yes.
Yes, ma'am.
Can you go to the guy's office?
Who?
Tanya Herrera.
Sure.
Thanks.
They can wait 2 seconds until we finish these last 2. They can like it. Okay. Number 6, you said we have 3 circuits. Do they share anything in common?
No.
No. So we just need to figure out. This first circuit up here has how many options? 4 options times this circuit has 3 options times 6 options. There's 72 total options. Guys, enough. I know. But sheesh. I'll have to beat her up later. All right. Take a look at number 7. How many different circuits do I have?
4.
I have 4. One shares. These two share a line in common. So we handle that first. Okay? So for this one, the top circuit has, the bottom circuit has, and they share one in common, so we have a total of 15. So these ones have 15 different ways that I can do this. And I have 4 different ways to take one off of this one, and 5 different ways to take one from this one. 300. There's 300 different ways that I can make a spanning tree from this picture. Okay. Questions? Okay, that is it for notes today. Your homework tonight, numbers 11, 12, 16, 17, and 18 in the book pages. You can also have the option to work on your Chapter 6 project. That is due next Friday.
No, I do homework. Me too.